Welcome to the Explainer. So if you're aiming for that absolute top tier, the A star, in your Cambridge Computer Science 9618 exams, you are exactly where you need to be. Today we're essentially cracking open the examiner's playbook. Because honestly, the difference between a solid B grade and a flawless A star, it almost always comes down to one really technical area: how well you handle expressions with arithmetic and logical operators. I'm going to show you exactly what examiners are looking for and reveal the precise strategies that'll take your answers from just good to totally exceptional.
Okay, let's dive into this. Here's our roadmap for today. We're going to treat this as your ultimate insider's syllabus. First up, mastering the core concepts. Then, top 3 examiner warnings. After that, the procedural framework, and finally, winning strategy, method marks. Let's get started. Section 1. Mastering the core concepts. When you finally sit down in that exam hall, keep in mind that Cambridge examiners have very specific expectations for this highly technical topic. Now, this brings us to a really fundamental question. It's actually one you've probably asked yourself while staring blankly at a tough past paper. Why do students find interpreting complex binary representations so hard? Seriously, if you've ever felt your brain tie itself in knots just looking at a string of operators and binary values, you are definitely not alone. It's notoriously tricky. But the real reason it's so hard? Well, it actually comes down to how we approach studying it in the first place. You see, there's a massive difference between superficial breadth and analytical depth. The syllabus is super clear on this. Top-performing students show a deep connected understanding that they can just pick up and apply to completely unfamiliar contexts. Superficial breadth? That's just memorizing the truth table for an AND or an XOR gate. We all do it, but it's not enough. Analytical depth, which is exactly what the exam prioritizes, means you actually know how to apply a bitwise mask to a specific byte of data just to isolate a single bit. It's all about logical, structured reasoning when you're faced with complex multi-step expressions. Moving on to Section 2, Top 3 Examiner Warnings. Since we know analytical depth is the goal, where exactly are students missing the mark? Let's take a look at the principal examiner reports to find out. Now, what's really interesting here is that these 3 major pitfalls, they're completely avoidable. First up, examiners note that students constantly confuse cause and effect. They mix up an input condition with the actual resulting logical output. Second, students always forget to check boundary conditions and edge cases. In computer science, what happens at the absolute limits of your data, like, say, an integer overflow in an 8-bit register, that is literally everything. And third, answers that aren't specific to the question's context. Generic textbook answers just won't cut it. So, to make sure you never fall into these specific traps, let's use a quick memory hack. I challenge you to invent a mnemonic right now, just using the first letters of those key terms. Cause, boundary, context. CBC. Maybe something like computers break constantly, or check boundaries carefully. Whatever clicks for you, lock it in. Every single time you evaluate an expression, just remind yourself, check the cause, check the boundary, check the context. All right, Section 3, the procedural framework. Now that we know exactly what to avoid, how do we systematically process these logical expressions without totally panicking? Let's walk through the standardized step-by-step sequence. Step 1. Identify the key elements. Basically, what specific operators and binary values are you even dealing with? Step 2. Apply the relevant Boolean or arithmetic principles. Step 3. Execute your analysis and do it with crystal clear working. And finally, Step 4. Verify your results. Just run a quick trace table in your head to make sure the output logically makes sense. Actually pulling off that 4-step process requires some really critical programming skills. You have to be able to accurately extract data from raw binary representations. You need to seamlessly perform calculations using operators, things like integer division or div, and modulus or mod. And then you have to draw solid evidence-based conclusions. The main takeaway here? This isn't just a math exercise. It's about translating raw binary data into a meaningful, actionable answer that the examiner can actually reward. If we were to boil all of this down into one ultimate triad for critical analysis, it's this: deconstruct, solve, evaluate. You break down the given information into logical pieces, you solve it step by step, and then you evaluate it to check